Well, welcome everyone, thanks for coming. Today's talk is about cycle trail decomposition for partial permutations, and hopefully if you've done some algebra you'll be used to the cycle decomposition for permutations, which I'll talk about shortly, and this talk is really just about how to extend that to the case where instead of total permutations you have partial permutations. This was originally going to be a talk at the Victorian Algebra Conference last year, and at the last minute I ended up doing a different talk. So I actually can't remember if I requested to do the seminar so that I could practice for that one sort of 6 months later, or if I did it after I did that thinking, well, I've already done these notes in a strange sort of Beamer package, and I didn't want to waste the effort that I'd gone to. So either way, this was going to be done here and wasn't. And I did try and update the title page today, but I sort of lost all the style files and things, so it was a little bit too complicated. So first, let me just introduce the things that we're going to look at. Permutations to start with. So the symmetric group Sn represents a set of all permutations of an n element set. And I'll generally use the set of the first n elements, 1 up to n, and write that set as just bold n, or n with an underline. So on the board, over here on the left, I have a permutation on a 10 element set. So this really is an element of S10. Let me call that alpha. Okay. And all it's meant to indicate is that 1 maps to 3, as you can see by following the line from the point labelled 1 goes down to 3, 2 maps to 2, 3 maps to 6, and so on. So you could put all of the information about the permutation just by listing the image of all 10 elements. But there's all kinds of other ways to do this. So one way would be to draw a little graph. So if I just draw 10 dots like this. Then what I do is just pick any old element, say 1, and I say, all right, where does 1 go to? It goes to 3. So I'm going to label the next one 3, so an arrow like that. Then I'll see where 3 goes. So 3 goes to 6. I'll call this one 6. And where does 6 go? Well, 6 goes back to 1. So I'll finish off like that. Then I'll pick any old other element. So it may as well be 2. Because that's the smallest one that I haven't used yet. And where does 2 go? Well, it just goes to itself. So I'll put an edge like that. Then 4 goes to 5, which goes straight back to 4. And then finally 7, 8, 9, and 10 look like this. So 10 goes to 9, 9 goes to 8, 8 goes to 7, 7 goes back to 10. So if you draw a graph from a permutation like this, you always end up with a collection of cycles. Right? The cycles might just have a single element like the 2 does, or it could have two elements in the cycle like the 4 and the 5, or it could have 3 or 4 or 50 elements depending on the permutation. And sometimes from that we write what's called the cycle notation, and we might write this as saying 1 goes to 3, 3 goes to 6, 6 goes back to 1, so we close the brackets like that. 2 goes to itself, 4, 5, and then 10, 9, 8, 7. Right, and that's cycle notation for the permutation. But typically we just leave off the 1 cycles, if you like, and that's a simplification there. Another thing that we like to do is, rather than write the permutation in just cycle notation, we'd like to split up the cycles. So the simplest kind of cycle are the 2 cycles, and these are called 2 cycles, like I just said, or they're sometimes called transpositions. Okay. And well, it turns out that you can write a 3 cycle as a product of 2 transpositions, and a 4 cycle as a product of 3 transpositions. Let me just tell you what the answer is for alpha and then try and explain why that's the case. 136 cycle, we can write that as 3, 6, 1, 3. I'll explain why in a moment. 4, 5, and then what do we have? 7, 8. Right, it was 8, 7 actually. For reasons to become clear later. 8, 7, 9, 8. 10, 9. Okay. So I've written alpha as a product of transpositions. And I just want to convince you, for example, that you can take a 4 cycle and write it as a product of 3 transpositions just by doing a simple example. So let's just, for the moment, go down here a bit. And I want to convince you that, for example, if I do a random cycle like a 5 cycle, I should be able to write that as a product of a bunch of transpositions. So this this 5 cycle sends A to B, B to C, C to D, D to E, and E back to A. And I'm going to write this as just a product of 4 transpositions. Now the transpositions are just found by looking at the order of the crossings in that 4 cycle. Okay, so if you were to try and achieve this 5 cycle with 5 objects in front of you, just picking up 2 and swapping them one at a time, you'd probably swap D and E first. So. And then D would be in the right spot. Okay, or it would have moved to the right spot. But E has only gone 1 step along. It's supposed to go all the way. So I'm just going to multiply it by enough transpositions, one at a time, like that. And ultimately I've done the right thing. So A, B, C, D, E equals D, E, C, D, B, C, A, B. All right, and obviously if there was only 4 of these things, we'd just sort of stop after or we just wouldn't have the first of these transpositions on the right. If there was more than 5, we'd go further. All right, so I hope that convinces you that the statements I've written up are true. I also hope they are true because I might have written things up. 3, 6, I'll tell you it looks all right. So any permutation, if you believe this, is a product of transpositions. Okay? But someone else might have written the permutation as a product of transpositions in a different way. And just looking at my list of 1, 2, 3, 4, 5, 6 transpositions, well, you might have written it as a product of 8 transpositions or 24 or something like that. It's a good question to ask. Is there some kind of way to work out if our products are the same or represent the same permutation without actually working out what the permutation is? Okay? And that's sort of where we're going to get up to on this. So the question is basically this: how do we recognize the 2 products are equal? Or not equal. So we'd like to be able to write down some kind of governing system of equations that are satisfied between all the transpositions that tell us when this, your product of transpositions equals my product, or if they're not. And that's what we're going to talk about on this first slide. So I'll go back to this presentation over here. So Sn is a set of all permutations, and as I've already done, I'm going to write I, j as the transposition that swaps I and j. So strictly speaking, this is a permutation that sends I to j, j to I, and maps everything else in a fixed way. And I'm going to call that Tij because I'm going to write down some equations, and it sort of looks a bit neater to write them in terms of symbols, like T, rather than brackets and commas. All right. Capital T is going to be the set of all of these transpositions. Now for every 2 elements of the set, 1 up to n, we've got a transposition. So we've got n choose 2 of these. So this set has size n choose 2. All right, And it turns out that this theorem, I'll explain the language or the symbols used, in some sense, encapsulates all of the information in saying that the transpositions make up the symmetric group, or the symmetric group is built out of the transpositions. So Sn equals, with these angular brackets, T, first of all saying that T generates S, so everything from generates Sn. Everything from Sn can be written as a product of these things. And I've written down three equations, or three families of equations, and the claim is that any equation that happens to be satisfied between these Tij's is somehow a consequence of these relations here. So let me just take a minute to talk about what those relations are, what they mean. So skip that page now. All right, suppose you were thinking of a permutation and it had, say, T35 in it, and then another T35 straight away. All right. So we're mapping three. We could have more elements, but let's just imagine we've only got 5. T35 remember switches 3 and 5 and maps everything else the same. So there's T35 and there's another one. Well, the net effect of this is, well, 1 just maps straight down to 1, 2 maps to 2. Now 3 goes to 5 and then back to 3. 4 just goes the same, 5 stays there. So this is really the identity map. And looks like there's a typo. That should equal 1. So you get the equation Ti squared equals 1. Okay? 1 is usually written as the identity map. So unfortunately, I've claimed that these things are idempotency, but you get a different semigroup for that. All right. What if in your product of transpositions you had T13 followed by a T45? Well, that would mean we switch 1 and 3, and then we switch 4 and 5. Okay. But you know, if you were changing the positions of things on the desk, it wouldn't have mattered if you'd done 4 and 5 first, and then 1 and 3. So T13, T45 should be equal to T45, T13. All right. So the second equation there, T2, means that basically if you've got 4 distinct subscripts, you can commute these things past each other. The last equation is a little bit trickier. I'll just write up a special instance of that. So for example, T1. In fact, let me just do it with the completely general case. So Tij, Tjk. So let's imagine we've got 3 points I, J, K. And let's do this product of transpositions on the left. I and J switch, and J and K switch. So the net effect is that we've got this permutation. That's a 3 cycle. Okay, what if we do it according to the second product? First of all, J and K switch, and then K and I switch. Like that. So that gives us the permutation like that, which thankfully is the same as the first one. And Ki and J. So ultimately, these 3 expressions give us 3 different ways to write this 3 cycle as a product of 2 transpositions. All right? And it turns out that somehow with all of these relations together, the correct versions of all of these relations, you can write any 6 cycle as a product of 5 2 cycles in all kinds of different ways. And in fact, if you wrote down a product of 24 transpositions that somehow equals the permutation I had up before, then somehow using these 3 equations you could transform your product into my product. assuming that they're both correct. Likewise, if you wrote down something that was incorrect, then there'd be no way possible to use these equations to transfer them. So this is all quite classical stuff. I don't actually know who this presentation is due to, because it doesn't seem to be proved anywhere, but it follows from other standard presentations, and you can prove it quite easily directly too. So the next part of the talk is about partial permutations. And you can probably imagine that, well, a partial permutation is just a permutation with some of the lines rubbed out. Or at least for finite sets, that's what a partial permutation is. So Sn is a set of permutations of the set n, and In is a set of partial permutations. Yeah, it's not Pn, although that would have been a decent name, but anyway, it's called the symmetric inverse monoid of n. And well, I don't need to talk too much about what the words there mean. So anyway, let's get a picture of an element from In. There's one. So this is actually just the permutation alpha from before, but with a few lines rubbed out, just to indicate that that's all we're doing. Taking a perfectly good permutation, rubbing out a few points. So let's call this one beta. And this is a partial permutation of a set of 10 elements. So this belongs to I10. All right, so what does this mean? Well, just like before, beta sends 1 to 3, 2 goes to 2, 3 goes to 6, 4 goes to 5, but 5 goes nowhere. So 5 is not in the image of this, sorry, it's not in the domain of this partial permutation. Likewise, looking at the picture, nothing gets sent to 4, so 4 is not in the image. Right? So if I write down the images of all, or the action of all 10 elements of the set 1 up to 10, certain things would be missing from the domain and certain things would be missing from the image. Okay? But nevertheless, it's still possible to draw this picture as a graph, like we did with the previous example. This sort of graph here with all the cycles, but something a little bit different happens. So let's see what we get. All right, if you look at the picture, 1 still goes to 3, 3 still goes to 6, and 6 still goes back to 1. So you actually have a 3 cycle, 1 to 3 to 6. Like 2 still goes to 2, so we've still got this loop. But now what happens is 4 goes to 5. But 5 doesn't go back to 4. In fact, 5 doesn't go anywhere. And nothing goes into 4. So we're going to have this component of the graph with 4 and 5 just as a path. It's not a cycle anymore. And then what else? 7 goes to 10. 8 goes to 7. But nothing goes to 8 and nothing comes from 10. So that's all we get for that component. Then 9 is also in its own little component, but it doesn't go anywhere and nothing comes to it. So it's not a cycle like the 2 is, it's just an isolated vertex. Right? It doesn't go anywhere and nothing goes to it. So what we end up with is a bunch of cycles plus these sort of path things rather than cycles. So the notation for that is, well, we still write 1, 3, 6 for the cycle where 1 goes to 3, 3 goes to 6, and 6 goes back to 1. Then we've got 2 there. But then with this 4 and 5, we still are going to write 4 and 5, but we have square brackets instead of round brackets to indicate that nothing goes into 4, nothing goes out of 5. But we've still got this sort of path from then one to the other. Then we've got 8, 10, sorry, 8, 7, 10. And finally the 9 is all by itself, and we put that in square brackets like that. All right. If we want, we can again cross out the 2, because that's, you know, any number that doesn't appear there, you can just imagine it goes to itself. But we're not going to cross out the 9 because it's quite important to know that 9 is different from 2. You know, it doesn't go to itself. It's kind of completely redundant. It's just sitting there doing nothing. Now, we called the product of cycles before the cycle decomposition, and this is called the cycle trail decomposition. Okay, that's a cycle, and these are trails. All right. Now the next thing we did on our journey before was we saw that we could write any cycle as a product of 2 cycles or transpositions, and it turns out that you can write any trail as a product of 2 trails. So sort of, you know, silly transpositions like the 4-5 where 4 goes to 5 but 5 doesn't go anywhere. So let me see if I can put this up. So right, 1, 3, 6, I already said it was 3, 6, 1, 3. Here for the 4, 5 I've already got a 2 trail. Then 8, 7, 10. Turns out that we can write this as, I get this right, 7, 10, 8, 7. And then 9 is a funny sort of thing that I'll just write up the answer and hopefully convince you that that is actually, for example, 10, 9, 9, 10. Okay, the 10 isn't important. All that matters is that we've got a 9 in the middle. Right. So let me see if I can convince you that a product, say a 5 trail is a product of 4 2 trails, by doing basically the same thing as I did before. So let's consider the trail A, B, C, D, E. So A, B, C, D, E. So A goes to B, B goes to C, C goes to D, D goes to E, but E doesn't go anywhere, and nothing goes to A. So that's my 5 trail. And basically I want to write this as a product of 2 trails. So partial permutations where only one thing gets moved, basically. So again, if you were trying to achieve this as a movement of things on your desk, the first thing you'd do is probably throw E off the desk, and then you'd move D to the position that E was previously in. So you do something like, leave those 3 the same, and then go, D can go to E, and E can go away. Then you might move C across, like so. Then we move B across, finally move A across, and we've achieved the desired outcome. And that's the product. So this one here is D, E. Then the next one down was C, D, etc. All right. But it turns out that you could alternatively have written this. So start with a DE. Now let me just change this picture here. If I put in these lines like so, then I could have actually written it as the 2 trail, D to E, and then the 2 cycle, C to D, and then B, C, A, B, if I wanted to. So there's actually a real wealth of possible ways that we could do this. If we didn't want to do it like that, we could have left out, say, this one, and actually make this trail instead of a cycle. There's a zillion ways to write a trail as a product of 2 trails and 2 cycles, if you want. So the question of whether a given product of cycles and trails is equal to another one actually becomes quite a lot trickier. Okay. Just wondering if I want to say something else about all of this.
You wanted to say why square brackets 9 is equal to...
Oh yeah, I should say why. Yeah. So earlier I claimed that 9 equals, what was it, 10? Well, let's see why. So if I start on the right-hand side, we don't really need the first 8 things, but if 10 goes to 9, and then we do 9 goes to 10, then that's what we get. And when we simplify that, we've got 9 missing and 10 just there by itself. So in fact, that's the right hand side and that's the left hand side. Right. But it turns out you can do something even more interesting, which is that in this product, apologies that this is getting a bit messy, but in this product here, I've got a mixture of 2 trails, these things with square brackets, and some transpositions. But it turns out that once you've got any trails in your product, you can somehow get rid of the transpositions and just put more trails in. So I can't just change these round brackets to square brackets, or that would somehow destroy the function. But I can somehow turn, for example, this 3, 6 into a product of other trails. So let me try and show you how we can do that. So let's use the fact that somewhere in our picture we've got this 9, and I'll try and show you how I can write this much as a product of some trails. Right. Now, let me draw that as, I'm going to ignore all the points apart from 3, 6, and 9, because they'll just be straight lines in here, sort of doing nothing. So 3 and 6 get swapped, and 9 stays the same. And I'm going to try and write this whole thing as a product of 2 trails. All right. So basically, the first 2 trail is going to have the point 9 missing. If any of the other points were missing, then we'd sort of destroy the fact that 3 and 6 do map somewhere. So 9 is going to have to go somewhere, and it doesn't really matter. We could do that. Now this hasn't achieved too much yet. We've made sure that 9 is not going to be in the image of this product, but we sort of mapped 6 to the wrong place. Right? But what we have done is we've freed up some space for 3 to map to the right place, like so. Okay. So now 9 is not in the image as desired. 3 maps to 6, but 6 still is mapping over to 9. But we can just sneak it back like that. So this is actually so 6, 9, 3, 6, 9, 3. All right. So back in that original product of transpositions and 2 chains, or 2 trails, sorry, I could replace the transposition by these 3 things if I felt like it. There's no way I'll remember that. But basically, these guys can be replaced with, it'll be a total of 6 So we can actually write the whole thing as a product of two trails. And in fact, if we did that, we don't actually even need the last two there. Okay. All right. I better not make that get any messier. So let me not write anything further at this point. I'll just go back to the slide. So this is what we've been fiddling with, I10 in our example. So let me introduce some more notation. We called the transposition that swaps I and j, Tij, and now I'm going to introduce some notation for the square bracket versions. It turns out that for the formulas that I'll write, it's more convenient to let, for example, Eij be the two trail that sends j to I and I nowhere. Right? Anyway, so basically we've got E24 will be the one that has 2 not in its domain and 4 not in its image. Okay. If I did E42, then we'd be going the other way. So you can actually see that E42 is the inverse mapping of E24 and so on.
Do you,
right.
I mean, your identity is a bit wrong, isn't it? I mean, it's not an inverse. When this, if you multiply those, you don't get an identity map.
Yeah, that's an excellent point. So imagine I did E24 followed by E42. Right? So E24 looks like that, and then E42 looks like that, which means that the product of those two things is this. Now say that it's the inverse mapping in the sense that it undoes what the other one does, but it doesn't leave you with the identity mapping. Rather, it leaves you with the restriction of the identity mapping. So this is the identity mapping on the set 1, 3, 4, plus 5, 6, 7, or however many points you've got. On the other hand, E42, E24 gives us this one. Which is another identity map, but it's an identity map on a different subset. So that's the identity map on the subset 1, 2, 3. All right. So not only did the product of an element and its inverse not equal the identity map, or the identity element of the semigroup, but if you take the product of an element with its inverse in different directions, you get different things. All right. And this is yeah, to explain further would be to get into the proper meaning of this thing that I call the inverse, let's just say the inverse semigroup, okay, which is an algebraic setting where everything has some kind of an inverse, but inverse means something a bit different to group theory inverses. Multiply an element by its inverse and you get an idempotent rather than an identity map. A single identity element. So anyway, if we let E be the set of all these sort of two trails, or whatever you want to call them, sort of partial transpositions, and remember now for every pair of elements from 1 up to n, we've got 2 of these. One that sends I to j, and the other one that sends j to I. I've tried to convince you that any partial permutation that has a trail in its decomposition is actually a product of just these guys. So we don't have to use any transpositions if we don't want to. And that's sort of summarized in the last point of this theorem here. So the first point says that the symmetric group is generated by all the transpositions. I hope you believe me that from before. The last point says that all the partial permutations that aren't actually total transformations can be written as a product of these two trails. Okay? And then, well, since everything from In is either actually an Sn or In minus Sn, it follows that the whole thing, In, is generated by T and E. In fact, something slightly better can be said. So I n generated by T and E, and in fact it's equal to the union of the sub-semigroup generated by T and the sub-semigroup generated by E. So this is usually not the case with, you can't just expand the brackets when you've got a generating angled brackets and a unit sign. But it is a case in this example. So basically, your whole semigroup IN has this SN bit at the top, and it's got all the rest down here. And somehow these form two perfectly good sub-semigroups in their own right. So you get this nice group up here, and then a even nicer semigroup down there. I'll contend. And well, the next couple of slides just give more information than this. So they tell you what all the relations are that you need with these things. So the next slide tells us what the relations are for IN minus SN. That's here. So we've got the generators corresponding to these two trails, and we've got these sort of slightly more complicated relations. But these relations are so sort of sensible. I'm going to draw up a few pictures of these. They look pretty messy, but they each have a very important story to tell. So let me start with the first one. Done. E1. So let's imagine that we do E ij squared. So I'm only going to put the points ij in, all the other points just go straight down. So ij means j goes to I. And if I do that a second time, then basically nothing goes anywhere. I and j do the same thing. If I did ej squared instead, then it just would have looked like that, which equals the same thing. If I did ij cubed, then, well, it doesn't matter how many extra of these you stick down at the bottom, it's still going to be the same thing. All right? So the first relation just tells us that basically you do one of these things at least twice and it just sort of kills everything. The next equation says that, imagine if I do ij, ji, then ij. And that means I go ij, ji, ij. So the line just wiggles to the left, right, left, which is just the same as that. Okay? And this is sort of what it means to say that something is a semigroup inverse. Basically, A and B are semigroup inverses if A equals A and B equals B. And to say that a semigroup is an inverse semigroup is to say that every single element has exactly one inverse in this sense. Right? Anyway, what's next? E3 says that if you take four elements, distinct elements like that, and do that map followed by that map, then it's the same as doing them in the opposite order. So just that followed by that. Okay. These are sort of the, when you're trying to prove a theorem like this, and you're trying to actually come up with the equations in the first place, these are sort of the obvious ones that you just write down. The ones later on are the things that you sort of get stuck with and wish that you could get rid of. Like the parallel posture. E4 says Eij, Ji, which looks like this. Ij should equal, what is it, Ik. Which means that we have to actually have a J somewhere. What does Ik look like? Ik, and then K, I, like that. So they're both just different ways of having I going nowhere, and the other two things going the same place. I'll skip E5 because that's sort of a technical, little bit technical. E5 just gives us 3 different ways of writing this one, or something like it. E6 is really interesting, so I'll put that one up. Actually relates to something that we've talked about already. So E, K, I, E, I, J, E, J, K. So basically we start with K and we kind of go through I and then J. What do we get for this one? So I, J, K. Ki means that, Ij means that, and then Jk means that. So what do we get? Well, the net effect of this is that K goes nowhere, I goes to J, and J goes to I. So this is one of these transpositions with a point missing that we looked at before. What about E, K, J, J, I, E, K, E, I, K? This time we go K, J, then J, I. So that was correctly. Oh yeah,
Just
sorry.
use opposite.
This one, the wrong way around. K should have a dot. Okay, then Ji means that way. So I change the order to make it convenient, and now I'll just make lots of mistakes. And then Ik. Okay. All right, good. So that is done. So there's actually 2 different ways, or 2 very short ways of representing this transposition with a point missing. And somehow it turns out that it's these kinds of words that play a huge role in the proof of this theorem. E7, if you look back at it here, you see that actually the first 3 symbols of E7 are the same as the 3 symbols from E6. So we've actually got the transposition at the start, and this sort of tells you what happens if you multiply a transposition by something else. Sort of, if something else goes past the transposition and just changes the transposition to something else different from so anyway, that's probably all I want to say, or all I really need to say about the IN minus SN bit. Just going back to the previous slide, I've told you about basically the symmetric group, the singular thing at the ends, and told you that the IN is somehow made up from those 2. And the completion of the story is that basically if you want to get relations for these things, you just put the relations for the E's and T's together, and then you put these extra relations that I won't go into that tell us essentially how to combine the E's and T's. Most of these, again, are pretty sensible, and in fact, actually no, that's incorrect. All of them are very sensible. All they are is that every single relation here tells you what happens when you multiply a T and an E, and it tells you at the right-hand side how you can write that just with ease. Right? So it's actually quite simple to get this from the previous ones, modulo as a sort of technical result. And that's the end. Thanks very much. Take a couple of questions, or if there is.
So James, when you're showing that you've actually got a presentation,
Yep.
You've got the generators, and that you've convinced us that they were true, and the relations, it's easy to see that all those relations hold, but you have to also show that there are no others, or that you
and
that must be the hard part.
Yeah, that's always a hard part. So so there's sort of three bits. You've first of all got to show that anything is a product of the generators.
Yeah.
You've then got to check that the relations are actually true.
Yeah.
And then, sort of philosophically, what you're showing is that any relation is a consequence of these ones. But practically what you do is you use these relations somehow to show that any product of these things can be written as a certain special kind of product that we call a normal form. And then show that if 2 elements just happen to give you the same partial permutation, then their normal forms must be equal, or at least easily transformed into one one into the other. And yeah, that's the bulk of the work. That's usually 90%. It's sort of fun coming up with the relations, and then it's a slog trying to prove that they actually work or that they suffice. But I think that's fun too.
So is Andrew's question actually about completeness?
Exactly, yeah. Yep.
So there's also a question about uniqueness, is there not? Because you've used a daring mathematical trick to use elements that weren't actually part of the action.
Yep.
To satisfy the complete path traversal.
Yep.
But couldn't you have done that another way?
Yes.
Even by using elements outside the permutation?
Absolutely, yeah. So when I just had 9 going nowhere, I called that 10, 9, 9, 10. But I could have called it 3, 9, 9, 3.
Or 11.
Or 11 or whatever. Although I shouldn't really use 11 if 11 is bigger than n. But essentially that's encapsulated in the relation E4, which says that if we put I equals, or say J, this is around the other way. If you put J equals, I equals 9, J equals 10, and K equals 3 or 11 or whatever, you get that there. So yeah, somehow you have to prove that however you chose to write your, the permutation and I did, somehow they're actually the same thing.
But if you chose to use the mythical 11 in all such instances, you wouldn't have the need for this.
Well, these are, so these have own, yeah, we could have infinity, right? So these are only with subscripts ranging over the integers 1 up to 9, 1 up to n.
Sure.
But yeah, I mean, certainly in the normal form, the way it worked is somehow you identify the maximal thing that isn't in the image or domain, whichever way you want to do it, and then somehow write all of those, say, transpositions with something missing, where the something missing is always this big thing. And that's one of the major challenges, to write an arbitrary word that might have 3 million E's jumbled everywhere into a sort of neat form, where you've got all these transpositions with, say, 11, if that's your favourite thing.
So then wouldn't it make it simpler to use a mythical extra element? Because you wouldn't have to go through all possible.
The problem with that, if I understand it correctly, and apologies if I don't, is that you end up working in a bigger semigroup.
But only for the purpose of doing the formal proving stuff.
Yeah, there might be some way to do that, but again, if I'm understanding you correctly, I think that would mean also that you possibly would end up mapping several things to n, 11 or infinity or whatever, which would mean you're no longer in the invertible, partial permutations, but in a transformations where different things can go to the same place. There could be some sort of sensible way to work that.
That's a very good defense.
Okay, that's my argument, where I'm just trying to win an argument. But yeah, you could have a good point.
I have another one. Thanks. So with the 9, the square bracket 9,
yep.
You're replaced with the 10, 9, 9, 10.
Yep.
So when you're reading cycles of permutations, I mean your group is acting on the right? So you're reading, you're taking your numbers and you're filtering them through. So okay, 1 goes to 3, 3 goes to 6.
Yep.
And that's how we're used to reading them for group theorists. But when you have that 10, 9, 9, 10,
yep.
You're asking, where does the 9 go? You're bringing it through the permutation, and it's the square bracket 10, 9. And so, well, that says 10 to 9, it doesn't say what happens to 9.
Yep.
But then you get the next one and says, oh, that says 9 goes to 10. So it looks, if you read it like that, as though 9 goes to 10. When you draw the picture, it's all clear. But do you have a mnemonic or like a way of thinking about it that? Yeah. So
you sort of start with 9 on the left and see where it goes, and then it drops off at some point.
Yes. So I mean, if you were thinking of it the way as someone who plays with symmetric groups would think about it, you'd say, okay, the 10, 9 thing is a function that sends 10 to 9.
Yep.
It doesn't have 9 in the domain. And then the next one is a function that sends 9 to 10.
Yep.
It has 9 in the domain. So 9, therefore, when you compose them, goes to 10.
Yeah.
But the thing is that, so yeah, maybe, do you think about that when you see the square bracket 10, 9?
Yeah, so you sort of got a situation where you might have the, I don't know, let's say E and F of these two things. Right, so A, B, C, D are just the first four transpositions or trails or whatever. And you sort of go, okay, 9 goes to maybe 8, and then it goes to 5, and then 8, and then 9. And then here, what happens to 9 here, it just drops off, and then you don't really need to keep going.
Okay.
Right, so that's just sort of, but I think your question is, if you were just looking at the A, B, C, D and these things, you sort of look at the last thing and say, well, 9 goes to 10, so maybe something's going to go to 10.
Yes.
But the point is, if these are all just transpositions, then everything's in the domain and range of each of them.
Yeah.
Whereas just looking at, say, the D one, its domain might be absolutely everything of itself, but A, B, C might somehow have killed 3 things in the domain. So
the 10, 9, square bracket 10, 9, you have to, so whenever your 9 appears in a trail at all, or at the end of the trail, you kill it.
yeah, so for example, if you were looking through,
I mean, if I have a 4 trail,
okay, if you look, the first time you see a 9 at the end of a trail,
yeah.
means that there's no 9 in the domain, in the image of that much, right? But then you might see that 9 actually goes somewhere in the rest of it,
Yeah.
and if 9 ends up going to 10, like it does in this case, there, then that would mean that in fact, at the end, 10 rather than 9 is not in the domain. Right? So if these are just transpositions, you can't sort of look at the last thing and the second last thing, for example, and say, oh, 10 goes to 9, so maybe altogether 10 is going to go to 9. Rather, it depends on what happened before it and also what happened at the end. Now that's still the same with trails, except there's also the additional complication that things might somehow drop out of the domain and or image. So yeah, you can look at the 10, 9, and that might give you some information about what happens from then on, but sort of something might have gone wrong before that. Or, I don't know if I'm getting to the heart of your question or not.
No, you are.
We can think about it.
It's a joke we heard in first year physics. How do you turn ice into steam? Well, you heat the ice. How do you turn water into steam? Well, you freeze the water. And then problem solved.
Yeah, that's good. Reminds me of a joke about a house that's not on fire with a fire hydrant that's got a hose plugged into it, and you somehow end up unplugging the hose and setting the house on fire to reduce it to a problem that you know how to deal with.